In this question, you will be using lower rectangles to generate useful lower and upper bounds of functions. Consider the graph of f of x is ln x. The lower rectangles of width 1 unit from x equals 1 to x equals n plus 1 are shown in the diagram. Show that the area of the shaded rectangle is ln 2 square units. Well, we can see the height of the rectangle here, and if this is ln x, and this is when x is 2, the height of the rectangle is going to be ln 2. The width of the rectangle, as we were given in the question, is 1. So the area is just going to be 1 times ln 2 is equal to ln 2 square units. By considering the sum of the areas of the lower rectangles, show that ln n factorial is less than the integral from 1 to n plus 1 of ln x dx. So, the area under the curve, that is going to be the integral from 1 to n plus 1 of ln x dx. We know the rectangles are under the curve, and we know therefore the area of the sum of the rectangles, because of these areas that are left over, is going to be less than the true area under the curve. So sum of rectangle areas, that is going to be ln 2, which is the area of the first rectangle as we showed in part A, plus ln 3 plus ln 4, and so on. The last one has a height of ln n, and therefore the area would be ln n. So that, using a log law, is ln of 2 times 3 times 4 times and so on up to n, which is ln n factorial. As pointed out, the rectangle sum would be less than the area, and so ln n factorial must be less than the integral from 1 to n plus 1 of ln x dx. Verify that the inequality holds for the case where n equals 5. So we can just calculate ln of 5 factorial, and that comes to 4.787, and we can do the integral from 1 to 6 of ln x dx. We're just evaluating on the calculator, and that would give us 5.751, and therefore we can make the statement that ln 5 factorial is less than the integral from 1 to 6 of ln x dx. So now we're moving on to consider lower rectangles of width 1 unit below the graph of g of x, which is equal to n sine pi x over 2n for x between 0 and 2n. Note the widths are still 1, and we can see this is y equals n sine pi x over 2n. By considering the areas of the lower rectangles from x equals 0 to x equals n, show the following inequality. Okay, so the area of the first rectangle, that is going to be 1 times n sine pi over 2n. For the second rectangle, we're going to get 1 times n sine 2 pi over 2n, etc. So the sum of the areas is going to be, well, we've got this common n that we can just take and put in front, and then we have sine pi on 2n plus sine 2 pi on 2n, and so on, up to sine n minus 1 pi over 2n. The area under the curve, well, that's going to be the integral from 0 to n of n sine pi x over 2n dx. And we can do that integral. That is going to give us negative n cos pi x on 2n. Don't forget the reverse chain. We'll need to divide by pi over 2n and evaluate from 0 to n. And if we do that, note that this will turn upside down and multiply. So we'll have negative 2n squared on pi cos pi x over 2n from 0 to n. So that's going to be negative 2n squared over pi into, well, that'll end up being cos of pi by 2, and then with the 0 in there, take away cos of 0, which is negative 2n squared on pi times negative 1, giving us 2n squared on pi. Once again, the rectangle's area is less than the area under the curve. So that is going to give us that n into sine pi on 2n plus sine 2 pi on 2n, and so on up to sine n minus 1 pi on 2n is less than 2n squared on pi. And since n is positive, we can just cancel off of each side, giving us the final result, sine pi on 2n plus sine 2 pi on 2n, and so on, up to sine n minus 1 pi on 2n is less than 2n over pi. Okay. Now consider the case where a function h is defined by h of x is 3 to the power x for x between 0 and 1. Let a be the integral from 0 to 1 of h of x, so that will be the area. By considering the sum of the areas of n lower rectangles of equal widths w, units from x equals 0 to x equals 1, show that a is greater than 2w over 3 to the w, take away 1. Well, very quick sketch of that, like this, where this is y equals 3 to the x, would give us these rectangles like so, where the width is w. But note, because the width here is 0 to 1, we're doing n rectangles. That is 1 over n 2 over n, so w is 1 over n here. So for the area of the rectangles, we are going to get w, and then let's think about these heights. That will be 3 to the 0. That will be 3 to the w, and then the next height here will be 3 to the 2w. So we're going to have 3 to the 0 plus 3 to the w plus 3 to the 2w, and that will continue up to 3 to the n minus 1w. So that is a geometric with a equal to 1, r is equal to 3 to the w, and n terms. So we'll get 1, 3 to the nw take away 1, times w over 3 to the w take 1. Now, using that is going to make that just 3, because we've got 1 over n times n. And so that is going to be 3 minus 1w over 3 to the w take away 1, which is 2w over 3 to the w take 1. So the area is greater than 2w over 3 to the w take 1 as required. Now for part 2, we want to find an upper bound for ln 3 in terms of w. So a is equal to the integral from 0 to 1 of 3 to the x dx. This is a standard integral, so that's going to be 3 to the x over ln 3 from 0 to 1, which is 3 over ln 3, take away 1 over ln 3, and so that is going to give me 2 over ln 3. So we have 2 over ln 3 is greater than 2w over 3 to the w take away 1. So that's 2. 3 to the w take 1 over 2w is greater than ln 3. And that will give me that ln 3 is less than 3 to the w take 1 over w.